Hi folks, and welcome back to Physics with Captain Rod. This video is meant to be kind of part two in a series here of how to handle distributed loads. So what I'm looking at here is we've got this beam and it has some sort of just generic distributed load that I've sketched on it. Remember that this load can be described as some function. Sometimes I sometimes call it a weight function. And that's what this W of x means. Now, this function normally is described with respect to some set of coordinates. I'm going to go ahead and just put that at the left end of the beam here. So we've got like an x, and we don't really need the y-axis for this. So in this coordinate here, the vertical distance here represents the value of this function. And you notice that this value of that function changes as we move left to right. As far as finding the net force on the board, or on this beam, that's done by breaking this beam into segments, right, of width perhaps dx, and then there's a force associated at this location due to this rectangle, and that force would point down, and that would be a dF. And the reason that's a dF is because this weight function, which has units of pound per foot or maybe Newton per meter or something like that, is acting over an infinitely small distance. That force is going to equal the function value here times dx. And again, remember, this thing's got units of pound per foot or Newton per meter or something like that. The total force is then found by integration. So if we add up all of these products, and again, that's W as a function of x, in this case from 0 to L, then we would get this. Now it's important to realize, as far as this graph is concerned, what is this integral giving us? So in this original picture, this integral is giving us this area bound under our weight function here. So this total force here is given by area. Now, the next thing is, what about our x here? Like, where does the force go? So that's found by setting the moment due to our distributed load equal to the moment due to our single force vector. So on the left-hand side, the moment of this force about this point would be the force dF times the distance x. That would give me what I would call dm, a moment of this force about this point, and it would be a dm because remember, this force is infinitely small. Now the df, remember, can be written like this. So the moment produced about this point by this force is going to look something like this. Integral, in this case 0 to L, but again this will vary problem to problem, and this is what I'm calling L. See, the df is our weight function times dx, so again that's just the force, times distance. Over on the right hand side, the moment produced is this force times x, and again that's not f of x, that's force times x. And typically how we find x is that we equate these two. We equate this to this. Now if this is some function, maybe a sine wave or parabolic or who knows what type, this is pretty well how you work these problems. But there's quite a few problems that show up quite a bit. Constant load functions, triangular load functions, and trapezoidal load functions. So what I'm going to do here is I'm going to pause this, redo my video, and talk a little bit about handle those very common cases. All right, folks, so I'm back. So the first very common case we're going to look at here is we're going to look at a case of a constant function here, where the loading, so many pounds per foot is considered constant as we move left to right along the beam. And again, the idea is we want to be able to put a single force vector here. We want to calculate its magnitude, and where do we put that force vector? All right, so the magnitude of the force is given by the area under this load curve. So this area right here, this rectangular area, is going to give us the magnitude of that force. And because this is a rectangle, its area is going to be whatever this height is, which I'm just going to call W, times whatever this length is, and I'll just call it L. Then the million-dollar question is, where does that force vector go? Now, I wish I would have talked about this a little more before I erased my function here, but if you go through the previous video that I made where there was a couple of triangles, and you'll find that what we discovered was that the force vectors go at the centroid of the load function here. So a rectangular load has a centroid basically right in its middle. So this load would give us a single force vector equal to whatever this length is times this height. That's the area under the load curve here. And it would go at L over 2 in this example. And that's how we replace a rectangular or a constant load function with a single force vector. I'm going to take a moment, pause it, look at another common case, or draw another common case up. All right, so I'm back. All right, what we're looking at here now is some sort of triangular load function applied to this beam. And again, the idea is we want to replace this loading with a single force vector. Now, if it's a triangular load, then the endpoint here is what I'm going to call a W max here. So this is going to have some sort of maximum value. This will typically be a number in most of these problems. So the force vector, the magnitude of the single force, we're going to get by, again, area bound under this curve. Because it is a triangular area, 1/2 L times W max. And again, I'll go through some numerical examples of what that would look like. And again, as far as where the force vector goes, it goes at the centroid of the load curve here. So the x value of the centroid of the load curve, because this is a triangle, is 2/3 of the way from the end, or 1/3 away from this other end. So force vector goes here at about 2/3 L. Or again, 1/3 from the other side, doesn't really matter which. So again, that's coming from the fact that the x coordinate of the centroid of that load is 2/3 from the corner, or 1/3 from this right hand corner. And again, you can go back, I've got several videos on centroids if you want to go back and review where those are coming from. So a single force vector that would replace this triangular load would have this magnitude, and this is where it would be applied roughly. All right, so I think what I'll do now is pause this again and pull up a numerical example to walk through. Hi folks, all right, so I'm back here and we're going to take a look at this numerical example. I've got this beam here. I pulled this out of the Hibbler text. Right? The Hibbler is the text I'm using for my current statics class. And we've got a pair of loads on it. We've got this triangular load, and then this load here, which is a trapezoid. And what I'm going to do here is I am going to try to replace this triangular and the trapezoidal load with a couple 3 force vectors. So if you give me a moment here, first thing I'm going to do is get myself a picture of this beam, or another picture of it. Oops. This computer's really good for stuff like this. And now what I'm going to do is take these one at a time. I'm going to start with this triangular load. So again, we could write a linear function and use differentials in math and integration to find the total net force due to this triangular load, and again, use integration and set the moment on the left equal to the moment on the right to figure out where the load goes. But instead, I'm going to take the quicker route and just say this, that the single force vector equivalent to this triangular load is equal to the area bound under this curve here. And it's going to go, because this is a triangular load, it's going to go 2/3 from the left or 1/3 from the right. So if we go 1/3 from the right, that's going to put it at about 8. So 12, I guess 8 would be about there. So I'm going to go ahead and draw a single force vector. And I'm going to call that just F1 here for a moment and write out what it's equal to over here, where F1 is equal to, we need this area right here. And because that's a triangle, the area is going to be 1/2 12 feet times this distance, which is 800 pounds per foot. Pound over feet. And that's going to be, let's see, 6 times 800, 4,800. Now these feet are going to cancel. It's going to leave us with pounds. So that single force vector that's equivalent to this triangular load is going to be 4,800 pounds, and it's going to be 8 foot from the left-hand side, because the horizontal coordinate of the centroid of this rectangle is 2/3 from the end. All right, now we're going to take a look at this thing. So this is a trapezoidal load, which is no problem at all. And again, there's a couple ways we could handle it. I'm going to just move this over to the left here. Method number one, we could break this up into little slivers, right, and say that each sliver has a width dx. We would need to write a function then that describes this, and then we would say that the force is equal to our weight function here times dx and integrate. But again, what I'm going to do is a little bit simpler. I'm going to use the fact that the force vector goes at or can be found by the total area under the curve. And also what I'm going to do is I'm going to break this up into two different pieces. I'm actually going to do this and pretend like we've got two separate loads here. The bottom load is going to be a rectangular load. The top load will be a triangular load. Let me take the rectangle first. So from here to here is 500. From here to here is 9. And the centroid of this is right at its center, so that's going to be 4.5 over. So we're going to have a force, which I'm going to call F2, equal to 500 pound per foot times 9 feet, which is 4,500 pounds. That force is going to go at the center of the rectangular geometry. So that's going to be about here. Whoops. Go ahead and make these look like really nice force vectors. So it's going to be basically right in the center here. There's my force F2. All right, now let's talk about the triangular load. I'm going to put this in red. This height right here in this triangle is the difference between 800 and 500. So that's 300 pounds per foot. So the area of this triangle is going to create a force that I'm going to call F3, which is going to have a magnitude of 1/2 times 9 feet times 300 pounds per foot. All right, which comes out to be 1,350 pounds. And again, the feet cancel, leaves us with pounds. And then it's going to go at the centroid of this triangle, which is 1/3 from the corner. So 1/3 of 9 is 3, so that's going to be 3 feet over. So that's going to be at 15 feet. Or 3 feet to the right of B, and this is 4.5 feet to the right of B. So it's going to go maybe about here. And that force is considerably less. Actually, it's about 1/3, so I'm going to shorten it up quite a bit for my picture. So there's the force vector F3. So what I've done here is I have taken this triangular load, replaced it with a force F1 equal to this magnitude, area under the triangle. Took this trapezoidal load and treated it as a rectangular load and a triangular load on top of it. Area of the triangle, or I'm sorry, area of the rectangle is 4,500 pounds. Centroid of the rectangle would be 4.5 feet over from B. There's that force F2, and again, that distance in this picture, 4.5 feet. And then what I'm calling force 3 is due to the triangular load, area 1/2 9 times 300 at a distance 1/3 from the corner, because of that's how you find the centroid of a triangle, which would be 3 feet from the corner. So that guy right there, that distance, 3 feet. All right, so anyway, the purpose of this video is to demonstrate how to fairly quickly find equivalent forces for distributed loads and to calculate where to put them. I hope that this video has accomplished that. Have a great day.